It's a great pleasure to introduce Elchanan, who will be speaking on semi-infinite cohomology and the BRST complex.
So, topic is going to be semi-infinite homology and I don't know, BRST complex, W-algebras. Okay, so I will start with a reminder about the what we did about finites, like finite W-algebras. G, semi-simple algebra. We had a definition of the associated W-algebra, finite W-algebra, that was given by starting with the universal enveloping algebra and then dividing by like making the action of the unipotent radical be given by some character, and then all of that taking n fixed points. So which can also be described as a T. So fixed points we are taking for homology, and here we have a quotient. So this is taking homology. N of G. Wait. I mean, tensor minus the it's like the one-dimensional representation corresponding to the character, and then so it's taking this to be homology, the algebra homology. So it's homology and then taking cohomology. And part of what we saw is that so this is a complex, but everything here is concentrated in degree 0. So okay, yeah, I mean, concentrated in degree 0. That's the main point.
So, principal case. Sorry.
So, yes, sorry. I guess everything I'm going to say today is about the principal. Okay. So the W algebra is supposed to be an associative algebra, and it's supposed to represent representations such that the action of like action of n minus the character acts locally. The action is locally nilpotent. And we had a filtration on the W algebra. So we had two filtrations. They had the PW filtration and a correction that was given by the Kashtan filtration. The associated graded is functions on the size f plus b over n. So yet again, yeah, this is the principal case. Okay, so now we want an affine analog of all of that. So I guess an affine, so maybe let's say affine analog, I mean, yeah. In the affine case, we had the algebra for a given event to be like a number. This is like a central extension of the loop algebra. And we had a definition of anyway, before I'm getting the definition. So when we say like a general idea of what we are trying to do is we have the world of algebras, and then we have a finite scale corresponding to the case of algebra, and then we have the world of differential algebras. So if we add freely a differential to a polynomial algebra, we get the jet algebra. So construction here, going from G to set of G, so it's add differential, and this is supposed to be the semi-classical case, and then if we want to make that so quantization, so the slogan is going to be quantization of jet schemes are going to be given by, basically the idea is going to be by the, like let's say that we take the loop of G, so G of T, and why this is considered quantization, like, so we need something non-commutative. So the point is that we consider the action of that on the vacuum representation. Let's say whatever. Intuitive representation from of trivial representation. We can think about elements in elements here acts by multiplication, and elements did I? Yeah, I think I sorry. No, actually, yeah. Those elements act by multiplication, and those elements act by derivatives. Which is like literally the case if we take K to be, if we take G to be K, just like a function. So we have everything that is in negative degree, it will just act freely by multiplying the element, and everything in positive degree will, commutation relation will give us a derivative.
You mean induction to like that, some central extension of the...
Yeah.
The thing downstairs should technically include the center. It's like JG plus the...
Oh, yeah.
Okay. So, and then what we saw is like a convenient tool to deal with exactly this situation when we have like the jet space, and then we have some elements in positive degree that are acting by derivatives. The general framework for that is the language of vertex operator algebra. So we saw that this vacuum representation has structure of a vertex algebra. And for a vertex algebra, there is a notion of module over a vertex algebra. There is a canonical isomorphism between modules over this vertex algebra and discrete representation of level kappa of the Kac-Moody algebra. So that is about the Lie algebra itself. Now here we started with the Lie algebra, but we get the W algebra by taking homology, cohomology. So what the object that we want, what we want to mimic the construction that we had there. So we want W algebra associated to G and K, or and kappa, to be something that behave like, let's say, the homology of and T of so we want to start with our loop object, so loop of G. That's our because we work in the world of vertex algebra. This is the analog, like the loop analog of U of G. And then we want to take something that looks like cohomology with respect to the loop of N. Problem need to define, I guess. So more words, and of T is infinite dimensional in two different directions. So we have a theory of Lie algebra homology. We have a cohomology for semi-simple Lie algebras, and then we know all of the properties. All of that works for finite dimensional case. Here, this is and so we have like the t goes to n goes to infinity direction and n goes to minus infinity direction. One of them is so when n goes to infinity, we have full limit, and when n goes to minus infinity, we have a limit. So it's both an int and a pro. It's a pro int object or int.
Pro end object.
Thank you. So we need to extend, yeah. And so homology, pointed that homology extends naturally, I guess, to pro object and cohomology.
Wait, actually, I think, sorry, the limit and the colimit should be switched, right?
The what?
The limit and the colimit should be switched. Like if you just write colimit instead of limit and limit instead of colimit, then it'll be correct, but with the indices unchanged.
Oh, yeah. It's in pro. Thank you.
Yeah.
Cohomology extends to int objects. So here we have both pro and int objects. So the problem is how to define this object is called cohomology. So this is the formalism of semi-infinite cohomology, I guess, which has a general definition in the case where instead of n, we're going to take g, but in the case when we take n, the definition is shorter and easier, so that is what I'm going to do. Yes, one more problem here that it's not subgroups. Like I mean, this is not a presentation as like a colimit and limit as this algebra, but I will write the correct limit colimit in a second. Yeah, maybe I will write it now. So, I mean, I'm gonna write ni going to be 0.5 e minus n and I. So by 2 gonna be limit over j of joint action t minus I. And this is a half sum of simple co-roots by 2. And t on which I'm going to denote by limit j over and I, just an notation for this object. So it's basically it's like here we're taking limit. So we take completion when we allow when we want the when we allow higher and higher powers. But when we take a joint action, we basically make it like start lower, start with smaller powers of t. And the special part about n that is not true about the entire Kac-Moody algebra is that entire algebra and T is a union of n I or I greater or equal than 0. So we start with just Taylor series and bracket T, square bracket T, and then we have a sequence of Lie algebras, and the union, they're not like they're not containing each other, but their union is the entire Lie algebra. So, so now I'm going to define, first of all, I said we need to define cohomology. I guess first we need to define the category of modules. So we're going to define Ni mod is going to be colimit of and mod. So yeah, I mean we have Ni was written as a limit of Nij. So the category of module is going to be colimit over the category of modules over an Nij, and then T mod is defined to be limit over Ni and I. Okay. Yes, one more thing is one more thing is that here I wrote it as a limit. We can also write it as a colimit. Okay, yeah, I mean we have.
So sorry, this colimit. This limit formula. Sorry. How do we make sense? Like, what are the transition functors if these are not contained in one another?
Oh, that's true. What? Sorry. What did you say?
Or not?
Oh, okay. Well, if they contain each other, either. Oh, sorry. No. They are containing. Yes. Sorry. Never mind. They are containing each other. Everything is great. Union of bigger and bigger subgroups. Yes. So transition functors are going to be forgetful functor, and so we have yes, this contains in that. So we have forgetful functor from Ni plus 1 modules to Ni modules. It will have a left adjoint induction. Ni plus 1. So since all functors have a left adjoint, limit when the transition functors are given by the forgetful functor is going to be the same as colimit when the transition maps are given by induction. So basically, I'm just defining the category of modules as colimit over I, of colimit over J, of modules over something which is finite dimensional.
The express complaint is not obliv.
I have no idea what it is. So
French, it's oublié. I think is maybe the
Yeah, I think it comes from Latin, which I
okay.
It's the same root as oblivion.
yeah.
Anyway, now that I have a definition of the category of models, I guess I can define. So the category of homology is defined as colimit. So I want to define a factor of cohomology out of a diagram of colimit, because I can write it as colimit. It's enough to write a factor out of each of the components separately.
Sorry, are you categories here? Okay, great.
Yeah.
Just check. Because otherwise, if like at the level of Abelian categories, these are sort of here, I guess, but DG categories, it's like a definition. That's the point.
Yeah.
You see what I mean?
Oh yeah, I mean, yeah, I guess needs to be justified why the like we get a DG category, why the heart of the DG category is what
But you would expect like,
naturally
smooth
call
representations.
category of yeah.
I think sort of the point is like when you have these pro things, like the colimit is naturally like the thing that's sort of generated by things pulled back from some finite dimensional quotient. So
Okay. Final definition of semi-infinite homology. So we need to define a functor. So I guess in this definition, there is a dependence on the choice of, I mean, in my choice of here of the family and I guess I started with this sub algebra that was like I fixed a lattice and then I started my system from zero. So when I take I equals 0 in the definition of ni, I just get the like the n square bracket here. And then I am taking limit or co-limit from there. So at least the definition, not all of the properties, but at least the definition depends on the choice. So this is going to be a functor from modules over and to vector or chain complexes. So this is the same as before. This is co-limit over and I mod. So I need to write a functor out of each one of them separately. Well, over each one of them separately, I already have a functor of cohomology. So the algebra cohomology. I coefficients in. So I just have usually algebra cohomology for this pro algebra determinants. So basically that was it. So if I'm taking I equals 0, this is going to be trivial. So all that is happening is I'm taking the algebra cohomology, but then for any index higher than 0, I am adding a twist. And this twist is making it to behave like homology. Limit. So, and two things I guess I have to add. So my notation, the determinant of whatever is in cohomological degree the dimension. It's like the dualizing shift that is in the dimension of our variety.
And sort of dimensional Lie algebra.
Finite. And Nij is finite dimensional.
Oh, Nij, sorry.
Yes.
Oh, yeah.
Nij is finite dimensional, and it's like it's exactly the lattice. Like,
What's the notation here? So there is Ni. So the J between.
I think that's a semicolon.
oh yes. Yeah. So I mean, I guess yeah, like what like what I said before was that like when we take I equals 0, we literally just have cohomology. And I guess here one reason to see like why cohomology is okay to define for in that case is because yeah, I mean those categories were defined by co-limit because that is the natural direction. Like the progressive functor is going in a direction so that the category of modules is a co-limit. So defining functor of cohomology is to immediately extend to Ni, and then using the left adjoint, we also extend it by co-limit to modules over the entire algebra.
This object is G-vect or is it just vect?
Vect as the chain complexes.
Okay.
Yeah. And I guess it is so. In general, we have like homology. This is I don't know, reality, some duality between that and cohomology with the determinant. So this includes the shift weighted dimension of G. So what we're doing here is we're taking cohomology all the way to in the direction of n0 or of n square bracket t, and then taking homology in the opposite direction. Which I guess is another explanation for the reason why in the definition of W-algebras we had a mix of homology and cohomology. I don't know why in the finite case, but at least here it comes naturally from the definition of cohomology.
Yes, because in the finite case, it's really endomorphisms of the kind of induced representation, right? So you see the
yeah, but for some reason, so it's two explanations, but I don't see the connection between them. One of them is it's endomorphism, so you get homology and cohomology, and the other one is just how we define cohomology.
They seem to be kind of for different reasons, yeah.
Yeah, but as we'll see, the finite case, you can get the finite case from the infinite dimensional. So,
here it's not an associative algebra at all, it's a vertex algebra, so.
yeah. I mean, yeah, I guess it's
well,
can also be an associative.
There's this
logical associative.
Yeah, that's a good point.
But what? Anyway, all of that about the definition of semi-infinite cohomology. Then I guess okay, so okay, in particular, we can, in particular, it makes sense to write a semi-infinite cohomology of our vacuum representation. And from there, we can try to mimic the finite dimension. I guess I have to define the character in this case, so it's fine. So this is like a projection to the maximal torus. So this is just a direct sum of vector spaces of like group of K. And finally, I will take.
Why do you keep track like in double hard bracket T as well?
What? Sorry.
Why do you have?
So again, in the definition here, I started somewhere. Like even in the definition of semi-infinite cohomology, I'm taking the determinant of Ni over N0. Yeah. I could start with N5, 6. Like this is a choice of where do I start? I don't know how canonical it is, or like what will happen if we will change it. But, I mean, I guess the filtration will change, but I don't know.
It changes, I think it's tensored by a line overall or something, but it's not a big. It's like the relative determinant of the two lattices or whatever.
Yeah, so I guess it's not that dramatic, but it's still part of the definition.
Here, the choice of arcs is kind of so.
I mean, there is. I don't know. Anyway, there is like some. in I will soon write things in terms of Clifford algebras, and then there is something about what representation of the Clifford algebra we're choosing, and the representation we will choose now correspond to this choice of lattice, but there will be other choices that are not isomorphic, and I'm not sure what is the interpretation in terms of infinite cohomology. But it exists.
Can I ask you a question? What exactly are the modules here? What is N of?
So if if you choose this definition, then you have to give a sequence of modules, and each one of them is induced from.
So it's like definition. We are not making any claim.
Yeah, I mean, well, but a claim is for example, I'm saying that it makes sense to talk about this object. So this object is a part of this category. You can see it because
I think it's in the heart also, so it's kind of
yeah.
classical.
Yeah, I guess I did not write any element which is not in the heart.
Wait, sorry. As NFT module, this is just a free module. It's V of GK.
Yes, but you can restrict the G hat module to an n variable.
Yeah, of course.
Yeah, I mean, I'm only using a single module, and then I'm going to take semi-infinite cohomology and get a vector space, and this is going to be the W-algebra, and that's it.
Maybe I could just make a comment, just to clarify. Like this, some DG category, the heart is like the category of kind of smooth representations that you know, like the usual. Or they're required to, T has to act locally nilpotent. Yeah. Other than that, it's just usual kind of representation of a loop algebra. But then the DG category is something slightly familiar. It's not quite like the derived category of its heart. Instead, it has some, it's sort of compactly generated by things that are induced from compact open algebras. So it's the T structure. You can have, there are objects in this category whose cohomologies in all degrees vanish, but are actually non-zero of DG category. So I think that's the reason why you have to be careful.
All right, so here is the main theorems, I guess. Theorem one. So we have here a complex in cohomology that is supposed to be similar to in the finite case of the making the character the n act as our character and then taking fixed points, and we had a result that it's concentrated in cohomological degree 0. So same statement here. Infinite cohomology. It's concentrated degree 0. And so we're going to call that the W-algebra. Again, W-algebra corresponding to like a principal element. So this is going to be page 0 of all of that. All right, again. And then again, in the finite case, we knew a lot more about W-algebras. We knew that they are deformations of functions on the what's that constant slice? I don't remember that. Yeah. What?
Slowly. Constant in the principal case.
Anyway. So here the claim is that we have something similar. So in the finite case, W-algebras were associative algebras. Our analog of associative algebras in this case has a structure of a vertex algebra, a structure of a filtered. Even though this is kind of not really something additional because every vertex algebra in our definition will have this filtration, but whatever. Filtered algebra with associated graded so it's going to be the Poisson algebra, but I did not define what is the Poisson algebra in this context, but functions on f plus
Filtration code.
so filtration, over every vertex Z-graded vertex algebra, there is the Lie filtration, which is filtering by the conformal dimension, like taking a bunch of generators and then allowing the total sum of, and then you have, I mean, I will write it explicit later, but there is a canonical decreasing filtration over any vertex algebra, and there is a canonical increasing filtration over any Z-graded vertex algebra. And yeah, I mean, I would.
And it's clear that it's bounded below in this case.
Yeah. Okay. So I guess I will start with theorem 2. I forgot to write that it's numbered.
Sorry, can you push the board up a little bit?
Sorry?
Can you push the board up? Sorry. Thanks.
So I will start with 2. So I claim that it has a structure of a vertex operator algebra. So yet again, the strategy in the finite case was one option to do that was to write it as zeroth cohomology of something that we already know that it is an associative algebra. So here, this is a semi-infinite cohomology of a vertex algebra. So what we need to do is to basically give a vertex algebra structure on the complex, construct a complex that computes semi-infinite cohomology, give it a vertex algebra structure, and show that everything is compatible, so that the cohomology will remain a vertex algebra. So that is the strategy. So a general thing. So I mean, for finite dimensional Lie algebra, the way we compute the algebra cohomology is using the resolution by the exterior algebra. My simple cohomology computed and so here algebra of the dual of G. In the case, so it's not true in general that we can compute semi-infinite cohomology using resolution similar to that, but it is true if our module is in the heart of the category. So if M is part of these categories, only only in cohomological degree 0, and we can compute semi-infinite cohomology using using resolution, using like tensoring with exterior algebra. So now I will write it more explicitly what that means. So cohomology, the semi-infinite cohomology was defined as colimit over collection of it was defined as colimit of Lie algebra cohomologies over a collection of finite dimensional Lie algebras. So for each one of them, what we want to do is to use resolution by the exterior algebra and then take colimit over that. So, and the statement is, I guess, that will work if M is in the heart of the category. first of all, so we have here a colimit. So I will start like the degree 0 element is just the algebra cohomology of vector 2 and bracket. Just this is like our n0. So this can be computed as so algebra of that. And then now when we go higher, we go to higher ni when we increase our Lie algebra. So we have here with respect to ni. This is again, this is like this complex is this is going to be same thing, but now here algebra of ni, and this is dual. And here we don't take dual exactly because we have here a twist by the determinant that so exterior algebra of the dual tensor with the determinant is going to be the same as the exterior algebra of the original algebra.
What's dual here?
Continuous dual. So it's like direct sum over like we can write it like I mean,
Is it the same?
It's like if and with this is like a limit of vector space, so you take the co-limit of the same.
Is it the same as n dual bracket bracket t?
Dual bracket bracket. And no, because this is going to be this will have a topology. The other one will be a discrete object. This is a limit of a vector space. So a limit will have a topology. It's a completion. Co-limit will just be a union of vector spaces. So I think co-limit we get semi-infinite cohomology. It's going to be computed using, so we have like a double resolution. So one cohomological and one cohomology. So this is the cohomology part because we are going in the pro direction and then in the in direction of, I guess, sorry, this is supposed to be, of course. So, and T over
Ask about shifts. So I guess in the first formula, in double brackets, T dual is placed in cohomological degree 1. Right?
you need to play.
Well, sorry, what I mean is when you take the exterior algebra, like what you're really taking is symmetric algebra of the vector space shifted by -1.
Oh, yes.
You see what I mean? So it's the grading on the exterior algebra there is really the cohomological grading.
Mm-hmm.
No, grading, you see what I mean? It's the way it is with the Chevalier-Allenberg complex. So then for the other formula, the second formula, which degree are these quotients in? And in zeros. Also, are they supposed to be in degree -1?
They are, yes, I believe so, right? We just take dual and usual duality of tensoring with the determinant and
So it's supposed to go off in both directions, right? So,
yes. I think so.
yeah. So this in double parentheses T mod in double brackets T is sort of, you should think is living in cohomological degree -1. All right.
Yeah,
I don't know.
I mean, eventually everything will be in cohomological degrees.
Right.
But
that's kind of a miracle, right? There's like a lot of cancellation. Like it's in general, it could be it's cohomologically unbounded in both sides. Yeah. Um, so now you wrote, we have a resolution of semi-infinite cohomology as, so I mean, I guess let's replace that with our actual object. So this is the vacuum representation instead. So here again, we have vacuum representation. So the strategy is to say this entire thing will have a structure of vertex algebra, and the differential of this complex will be compatible with the vertex algebra structure. So when we'll take a homology, we'll get a vertex algebra. We already have a vertex algebra structure on that. And those are and those are exterior algebras. So if we have a tensor of two exterior algebras, there is a natural structure of a vertex algebra on that, which is called the fermionic vector.
Algebra or algebra?
Super algebra. Vertex super algebra. But I'm gonna write that and short annotation. And the statement is that this is going to be just a tensor product of a well-known vertex algebra, a vertex super algebra. So here is how to write it explicitly. So vertex algebra structure. So to the basis for n. So so first of all, so maybe a reminder, to give a structure of vertex algebra, we need to give for each, so we need to give what? We need to give a vacuum vector, we need to give translation operator, we need to give grading in our notation, and for each element in our vector space, we need to give a field. And all of those fields are supposed to be compatible with it, supposed to satisfy a bunch of properties. I guess the most important of them is locality, which means that their commutator is supported on the diagonal. So I will start, I guess, define the fields. So I guess first, okay, so I mean, why define the field? So if this is a basis for that, then a basis for that will be dual of elements here, tensor T to the n. So psi alpha n. And then there is a basis for the dual part. So this is n. So those elements are for any, in our vector space, those elements are for any n greater than 1, and those for any n greater or equal to 0, for any n greater or equal to 0. So first I will define the fields that correspond to
the theta correspond to psi alpha minus 1 and psi alpha minus 1 of the dual. So those are going to be which I will write by. It's just going to be the sum over all n. So it's very similar. Like it's very similar to the formula for the vertex algebra structure or for the Kac-Moody algebra. A minus n minus 1. And the dual, almost the same. The field corresponding to the dual element is going to be yet again sum over all of n, but there's going to be a shift by 1 because here we don't have the 0 element. We start with minus 1. It's just not very important. So those are our fields. And okay, I guess we need explanation. So usually when we write a field, we have a power series where we run over all z, and then the coefficients are endomorphism of v. So I need to explain why those are endomorphism of So I mean, for n less or equal to 0, those are just elements of our vector space. So the action is just by the wedge product. But for n greater than 0, you're going to add, which is what I said before. This is the general idea in vectors algebras. The elements with positive degree are going to act as like derivatives. So here are the commutation relations. All of those elements.
Why with no stars? Shouldn't we have positive powers of? You identify star with like negative powers.
Hey, yeah, this is supposed to be.
Oh, wait.
This is supposed to be fine.
Oh. Yeah.
Yeah, I mean, we just use the duality between that. Like we present that instead, that we think about it as that. In all of the indices, which is kind of missing everything, but in the various algebra literature, instead of writing that, you'll work out it like that using the residue pairing. The indices will be positive in both directions.
Why don't you write E alpha star?
I'm taking the dual element of the basis here. Star is just, I'm taking a basis for that and a basis for that. The star is a basis for that, and the double star is a basis for that.
They told me it's not the same as n star.
What? Oh. Yes.
When you say it's not the same as n star bracket.
Yeah.
We've written it's a basis for n star bracket.
But here,
I think maybe it should be E alpha tensor n star. Like the. Does that make more sense?
No, because you're identifying it by the residue pairing, right?
Yeah, there has to be a residue.
And I think when he writes it like this, he's using the identification. I think this is correct as written now, but I'm not sure.
Second line, I'm just confused because that's an element of in dual tensor or like in dual double brackets T or something like that, right?
yeah.
That's not the same thing as we just said, right? Rather,
Oh.
see what I mean?
Well.
So in double brackets T dual, as you were saying, via the residue pairing, identifies with in dual tensor like K double brackets T mod or K double parentheses T mod K double brackets.
Yeah, that's
T.
right.
Oh,
So I think it should be like E alpha dual, E alpha star tensor T to the minus n as well.
I see. We look at both of them.
And we're using
as written in this form.
Yeah. But the first one will be like in dual tensor, the the kind of polar
Yeah.
right? Yeah.
Sorry, the notation is currently used starts with -1 and goes in negative directions. So it flips. The initial notation was correct. T to the n, and then you use only negative n.
We want elements here to have negative index.
So if you use residue pairing, you have to use positive powers of n.
So, yeah. So it's good, but n is negative. Yeah. Okay.
Yeah.
Great.
Yeah, I guess. All right, amazing. So with all the indices in place.
I'm so sorry for starting this.
If psi and psi will all commute with each other, same with psi star psi star. And then this beta m star will be, so this is supposed to be like, this is supposed to be like, I don't know, t to the, this is supposed to be ti, and this is supposed to be dti, so be like delta, beta, delta, and so 0, except if this m minus. So like elements in positive degree in psi will act on element in negative degree, in the opposite degree, like negative here. On our and when this is with negative degree, this is an element of our vector space, and the action will be the element of square. Yeah, so this is the definition of the fields, and then okay, and then I will just say a general idea of why this is enough. I get okay. I need to define. So I mean, I define field, so I need to define a translation operator in degrees, and then explain why this is enough. Give a structure of vectors algebra really quickly, and then break. So, okay, I mean, I guess we'll have the vacuum. I also need to define a vacuum vector. So maybe is going to be okay. Yeah, I mean, I guess I need to add somewhere. Oh yeah, I mean, okay, yeah. Then translation operator is defined by on the vacuum vector. It will act by 0, and the commutator with field is going to be minus and minus 1. And finally, minus and minus 1 star alpha. Amazing. So, and Z grade of both of them is going to be minus 10. So maybe I remark this grading. This is going to like the PBW grading, and then we'll have to change it if we want things to work. But this is the initial definition. So yeah, and then just a few words on why this is enough to define it this way. There is a general principle in theory of vectors algebra, which is like the reconstruction theorem. Which basically says if we have a vector space and we have some collection, let's say finite, some collection of vectors, and I define what are the fields corresponding to those vectors, such that the coefficients of those fields are going to give me like a PBW basis for the vector space, then the structure will extend uniquely. So I really only, like similar to the Kac-Moody case, where we only really need to define the field corresponding to the like the element of G, of like x tensor t to the minus 1, and then everything else will extend uniquely by the axioms of vectors algebra. So I guess I'm not going to write the reconstruction theorem, but I will just like give an example. Let's say I have V1 and V, and I have some fields Vi, Z. such that and it's going to be written as sum vi n minus n minus 1, such that those elements PBW basis for V, then there is this operator, the unique vertex operator algebra structure on V extending those fields. So for example, like how this extension works, so we already have the fields corresponding to vectors Vi. So now what happens if I have like the I minus 1 and the J minus 1, what, sorry?
The I and 1 dot the I1 and 1 dot V I K and K applied to vacuum. Right now you're writing endomorphisms. It's cannot give.
Oh, yeah. I mean, yeah, like we need to go under like a vacuum vector. Yeah,
The previous time, so it's
need to also have vacuum space, and then we need. So when I'm saying it gives a PBW basis for V, it means that if you apply those endomorphisms again and again to 0, it's going to give me a basis for V, and it will look like a PBW V. It will be a unique way to write it. So like, for example, this one is going to be, the normal ordering. Normal ordering is basically designed so that field corresponding to a product will be the normal ordering of the product of the fields. All right, so what do we have so far? So we have a semi-infinite cohomology. What we want, our goal is to say that it give a vertex algebra structure on the cohomology and show that it is in degree 0. And we have the resolution of the semi-infinite cohomology and a vertex algebra structure on the resolution. And I guess, so, okay, I mean, now in the finite case, the way to show that it is concentrated in cohomological degree 0 is to say, we know what is the associated, we have a filtration, we know what is the associated graded, we can compute the cohomology of the associated graded, and it's going to be in degree 0. So a spectral sequence argument will give us that the cohomology of the original thing would be in cohomological degree 0. So we need here a filtration and the relevant structure for the associated graded. So filtrations and some vertex. So yeah, I mean, maybe a reminder. So a commutative vectors algebra is a one where like fields only have negative degrees. Positive degrees correspond to the polar part because of all the indexes are upside down. So algebra is a vertex algebra that all commutators are 0. Yet again, because in the formula for commutators, we will only have positive degrees elements, which correspond to polar elements. So this is like everything is regular, and there is like an equivalence of categories between commutative vertex algebras and just commutative differential commutative. So the factor in this direction is to take the -1 product. negative -1 component and endomorphism and acting with this element, and in the opposite direction have like, I don't know if I have A and B. So now I need to give for each element in A, I need to give a field, say T. So this by you see it's going to be X T A. So this is basically like we have a commutative product here, and we have this differential. So we have Taylor expansion. So we are taking a Taylor expansion of multiplication by A. What is happening? So an example of the, I guess, typical example of, or the free example of a commutative vectors algebra or a commutative differential algebra is the jet. Example. Commutative algebra. And it is a commutative differential algebra. And therefore has a structure of a commutative vectors algebra. So maybe one more thing. So basically the statement here is that the negative component corresponds to the commutative part. The positive components correspond to like the Lie algebra part. So that all the commutators are supported on the Lie algebra part, on the singular part. So a Poisson vertex algebra is similar to a Poisson algebra in general. We have a combination of a commutative and a Lie algebra. Algebra is a commutative vertex algebra. So we have a commutative product. So I'm going to denote it by C, Latvian translation, and then y minus, because it's only negative components appear, plus map curly bracket or y plus from the tensor phi to this. So we basically add a separate. We have all the negative components, and then we add a separate all of the positive components. If the index here is negative, then the coefficient of the endomorphism is positive. And such that all coefficients of y plus a are derivations of the commutative part. So we have a map similar to the usual map of vectors algebra, satisfying very similar axioms. All the same axioms, just here we only have positive components. And then all we ask, the compatibility that we ask with the existing commutative multiplication is that those will be derivations. And then just like in the, or maybe I will do example. So, as before, so the jet space that was a commutative differential algebra, but the jet space is supposed to be like a deformation of the loop space, which is non-commutative. Loop space is supposed to be a deformation of the jet space. So the jet space is supposed to be the limit of a non-commutative thing, so it has a Poisson structure. Example. Poisson algebra. this is going to be the vertex, or how the structure of a vertex Poisson algebra. Basically, because in the jet case, the differential is fully generated, and part of the axiom of vertex operator algebra is how it behaves with respect to the differential. So we'll determine it uniquely. And then, again, in the classical case, Poisson structure, the formation of Poisson structure is a non-commutative one. So, or an associative algebra with a commutative filtration will give a Poisson algebra on the associated graded. So here is the analog here. So definition, a good filtration. In this case, increasing filtration on a vertex operator algebra V. So of course, yeah, we have an increasing filtration on the underlying vector space. And so now we have two axioms that basically, first of all, we want the product to be compatible with the filtration, which means if we take an element in a given degree, its entire the corresponding, all of the coefficients of the corresponding field will be in equal or bigger filtration. So for each n, we want that. So this notation means I start with an element here, I take the corresponding field, I take the nth component, this is an endomorphism, and I apply it here. So I want for each n, I want to be able to do that. But second, we want the filtration to be commutative. So this is for all n. So if you want it to be commutative, we basically want all positive degrees elements to die in the associated grade. So we want that q minus 1 of v for all n greater or equal than 0.
So remind me what that means, like to take the nth component and apply it to fq.
Yeah, you start with, it's a collection of all elements of the form. An element here, take its nth coefficients in the corresponding field. So A and apply to B for A in FQB and for B in so FP. Yeah. And this is, so if you have A, an element in the vertex algebra, you have a field corresponding to A. You write it as like a power series. The nth component is AN.
Yeah.
An endomorphism of V.
Yeah.
Apply this endomorphism to B.
Gotcha.
And it's just two axioms that ensure that. Example. And this is, yeah, the example I promised about filtration. This is Lee's being with Li. Of all different in missing illustration. So if V is like a Z-graded vertex algebra, so we can write it as for all. And this is like for all positive number where this is the eigenspace. So I'm not sure if we require that or not, but definitely in the case of a conformal vertex algebra, where we have an operator, a grading operator. So we have an element here called L0, such that the commutator with this element is the degree. So this is the collection of all vector. This is like the delta's eigenspace. Then we can define ft of v to be span of elements of the form. So A1 plus 1 dot 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 A1, all that applies to vacuum. So for any n greater or equal than 0, and we need the sum of the conformal weight, like what the degree that my element is in, of I to be less or equal than. So that is the definition. In practice, here is like, example of the example for Kac-Moody vectors algebra. This is just the PVW. So it's basic, yeah, I mean, like, in simple examples, all that is happening here is we literally count the elements that we are allowed to make, just a bit more complicated. But because we are allowing minus nr for each n, we're basically allowing all of the span of my element. Like if you write my element and then you write the corresponding field, you will use like, I have one generating element, then that will give me all possible elements that can be written with one letter. So it's very close to the PVW.
Does the Kajdan filtration appear?
Sorry?
Does the Kajdan filtration appear?
Yes, it's going to be difficult. So we have a filtration on our vertex algebra, on the Kac-Moody vertex algebra, and we will get an induced filtration on the cohomology. In the wrong filtration, we will correct it. The result will be a filtration on the cohomology, and that will be the filtration on the W-algebra. So another hint that, I don't know, this is a reasonable definition. So yeah, I guess the whole point of that is theorem. And lead again. If we have a good filtration, if that is a good filtration, the associated graded is a Poisson vertex algebra. All right. Okay, so now we have a resolution. We have a vertex algebra structure on the resolution. We have a filtration, even though it's not a correct filtration, but close enough. And we can take the associated gradient. So the next step in making an analog of the classical case is to compute the semi-infinite cohomology for the associated graded, and then show that this is in cohomological degree 0. So, but the problem is, of course, yeah, we need everything to be compatible with the vertex algebra structure. So,
what does that symbol mean? Summation delta AI less than.
Oh, so yeah, this is a terrible element. Like you take span of homogeneous elements.
Sorry.
Take a span like AI.
Yeah.
Is a homogeneous element in conformal degree delta, and this is the notation for the degree.
So use delta for a degree.
Yeah, I have no idea why, but this is the usual notation for some reason. Delta is the I wanted to see. Okay, so yeah, I mean, I guess now it's going to be S3. So back to the finite case. We had a definition of W-algebra corresponding to semi-simple algebra. This was a cohomology of homology. Writing it plus twist. So we have here homology and a cohomology. So we can do same game as we did in the affine case, which is write a double resolution for that. So for CG, it's going to be UG tensor tensor N. And then, yeah, we have to compute the differential and everything. And then I guess, the insight of the BRST complex is that we can, in this specific double complex, we can describe the differential as like the adjoint action of a specific element. That would be useful for us because the adjoint action of an element in a vertex algebra is something we have control over versus just a random differential.
What do those letters mean? BRST.
I have no idea.
They're people's names.
Yeah. Okay. So here is how to do that. So each one of those elements is a representation of n, but the tensor product is also a representation, and there is a nice way of writing down how this is a representation of n. And this is using Clifford algebra. So that is the underlying vector space of the Clifford algebra associated to n plus n dual with the pairing, which is the usual pairing between a vector space and its dual. So the representation of this tensor product comes from the algebra homomorphism from n to the Clifford algebra of the direct sum with the formula given by so if x alpha, this is going to be a basis. So alpha is like a simple root that will go to just decomposing it with respect to the basis. So x alpha, x beta, x beta 2. So, the statement is that this is this representation. So now, in this complex, what we are doing is we are trivializing the representation, and we are identifying, we want to identify the action of n with the action of the corresponding character. So, forget about what I said. So first of all, this is the n module structure on that. So the n module structure of this entire thing is going to be given by n module on C of G is again going to be given by be induced from a homomorphism of Lie algebras. And this time it's going to be or induced from, I guess, is more correct. So it's like a morphism that sends that to apply to x. This is like the moment map, dual of the moment map. Minus and 1 plus 1 rho. So it's just standard representations. And then finally, okay, so this is the structure of that as an n module. This is easy to write down as the adjoint action of a specific element. And this element is going to be, so define U is going to be sum of eta x alpha tensor x alpha 2. So yet again, all that is happening here, we decompose things to respect to a basis. And that with the statement of the BRST reduction complex something in the finite case is that this is the complex computing finite like W finite corresponding to G. So
Sorry,
again,
what is mu?
The moment map, the dual of the moment map. Just like so from N to G, it just then.
Okay.
Yeah. Nothing happens here. It's like embed N into G and this notation. So anyway, to summarize all of this happening here, we write explicitly what is the modular structure of that. We realize that it comes from a morphism of Lie algebras, and then we can write down explicitly a differential as the adjoint action of specific element.
Of X.
Sorry?
Theta of X. On the right.
The Clifford algebra.
This one is this map. So the map of Clifford algebra representation, you start with an element and you decompose it with respect to a basis.
Yeah, but Q belongs to like the 4 times tensor product, yes or
no? This is plus. So here.
No, so theta is.
Oh, this is not supposed to be tensor. This is supposed to be times. Sorry. Thank you. Okay. And I guess, yeah, I mean, and then from this perspective, it's, I don't know, maybe easier to see the point of the cache-down filtration is we want that to have degree 0. So we need to correct the PBW filtration with this element. So with respect to the cache-down filtration, the adjoint action of Q will have degree 0. This will be important also in the affine case. So affine case, I guess, part of the reason of why it is useful to use the line with the vertex algebras, because a very convenient way of translating things from the semi-simple case to the affine case is to just rewrite the formula in terms of fields and then see what happens. Let Q of Z is going to be Z. So I basically, every element that I have in the semi-simple formula, I'm just thinking about it as an element in degree -1 and taking the corresponding field, writing down the formula again. And this is again a field. I'm writing an expansion of this. So I'm going to denote its component by Q of N. And then the 0th component of a field is like, in a vertex algebra, the 0th component of a field will act as an automorphism of the vertex algebra. Exactly because it cannot have, it will commute with everything. It will, in the commutator will not have any positive independence. Then take, we take the differential to be Q0. So we'll take our complex is going to be so this double resolution with Q0 is the semi-infinite complex. And basically for the same reasons. But then yet again, the problem is that we need Q0 to have degree 0 if we want that to be a morphism of vertex algebras. So we need to change, yeah, I mean, not if we want to be a morphism. we want the cohomology to be a vertex algebra. We need Q to be of degree 0. So
of a field is you apply theta to each coefficient.
yeah, you take X instead of that, you take the field corresponding to that. Field corresponding to that, field corresponding to that. It's literally repeating the instruction, but adding a bracket Z. So order for the associated graded vertex algebra, vertex operator algebra, we need that to have degree 0. And this is the downgrading or down filtration. So we just correct the grading. We add degree X alpha n. So this is like the real coefficients corresponding to the field to elements in U of G. So this is going to be same thing, but we add a component like the usual case. So we add that, and then we push down degree of the dual element is going to be corrected by minus applied of some of simple coordinates. So with respect to this filtration, Q0 will have degree 0. So we will get a vertex algebra structure on the associated graded. So in theory, we're supposed to now compute semi-infinite cohomology for the associated graded, and then deduce and see that it's only in cohomological degree 0. Deduce the same thing for our of the semi-infinite cohomology without the associated graded. The problem is that we want to use spectral sequence argument to say cohomology with the cohomology of the associated graded. For that, we need our complex to be bounded. Because of this component, our complex is not bounded. We can have if this can be positive, we can have this can be negative. We can have as large like element as large as we want. So vector sequence might not converge. Then depending on whether or not I will have time, I mean, the solution for that, yeah. It's kind of a technical thing, and the solution for that will be to find exactly say all the elements that contribute to unbounded degree will not contribute to the cohomologies. But before I get to that, I mean, I guess the step was like compute the semi-infinite cohomology of the associated graded and then deduce it. So first of all, we need to compute the semi-infinite cohomology of the associated graded. So here's the statement. Semi-infinite cohomology of just the associated graded, but now, yeah, of course, like the associated graded with down filtration. Is going to be functions on the jet space of the what? It's the slowly. Anyway, this space. Anyway, the jet space of that. Anyway, this is the statement. And the proof is almost the same as the finite case. So we yet again write resolution. We use the fact that everything is in the Hartwig category, so you can use the resolutions. So we use the usual double resolution. Located graded of that. Round bracket for the square bracket.
Sorry, your GUR of boldface V corresponds to this PBW filtration.
No, take it out filtration. Change the filtration. So I guess we start with we start with the homological direction. So we start with this component. So what else do I need? I need that this one gonna be so yeah, I mean this one is just functions on the jet space of the dual Lie algebra. This is again because the grading was the PBW filtration. And when we take like this resolution, basically corresponds to restricting to the locus where the n star equals chi equals our differential. So, as we said, in the finite case, we saw that. So we have jet of G star to jet of N star. So the first component is basically computing the causal resolution of restricting to the inverse image of chi. I mean, yeah, the statement here is it's kind of like we have a double resolution, and then we'll realize that one step of the resolution was to take a quotient by some subspace, and another step of the resolution was to take the algebra cohomology. So not very deep, it's just doing the computation. So we already saw, like, I mean, we're looking at inverse image of chi. And this complex so in the homological part is causal the post. Oh yeah, no, that was. So without taking the jet space, we saw that this is in cohomological degree 0, like this is a regular sequence. So we just applied jet to the same construction. So still in cohomological degree 0. Motion. And yeah, basically the way to write down the sequence corresponding to the jet space is to write down the same equation, define the subspace, and just make them polynomial, like power Taylor series in T. So cohomological degree, considering cohomological degree 0, and then the second step is to compute the algebra cohomology. So yet again, it's almost identical to finite. So then we have the same decomposition of the just use mu as a product of A and so the remaining complex. So now we have functions on that tensored with the cohomological part. That computes the algebra cohomology of the inverse image. You inverse
always
chi.
have this product of jets is the jet of the product.
So yeah, this is just homology of jet of n. I'm writing square bracket and jet. S, and so this is it, and this is just C, so the functions are. So yeah, not a lot happened. It's just a statement that things work just as they work in the finite case. The problem is, of course, with the problem is with the doing the next step, which is saying, okay, so now the also without taking associated gradient, it's going to be concentrated in cohomological degree 0. So for that, we needed our complex to be finite. Oh yeah. So we needed to deal with that. So we had a problem that this could lead our complex to be unbounded, not could. It will make our complex unbounded. So the vector sequence might not converge. And solution for that is, yeah, I mean, I'm not going to prove it, but I'm just going to say what we're doing. So we are going to embed, like we're going to have a subcomplex that is generated by those elements. And it will, its cohomology will be 0. And it's just like decomposing the complex into two complexes. So okay, I guess we had the algebra math. I'm now writing in the finite case, and then I will say what is the. In the finite case, we had a map to our complex. Like this was the map that described the representation. So can extend. From the entirely algebra to G. Basically, by the same formula, an element here will go to the decomposition of that with respect to a basis, tensor. I don't know what the formula. I mean, you just use the same formula. This is not going to be a homomorphism of Lie algebras, but at the restriction of that to the negative B is again a Lie algebra homomorphism. And now, yet again, we're doing the same trick of when we move to the affine case and work with vector algebras, we just take the same thing and just take fields instead of instead of elements in the Lie algebra. So when morphisms of vertex algebras. So from the Kat-Moody vertex algebra corresponding to N, this comes from this component, this is a part where we already have. And another morphism from of the minus some modification of the level. So all the statement is saying is that the inclusion of elements, like we can have those elements of this form as like as like the image of some Kac-Moody Lie algebra, Kac-Moody vertex algebra, sorry. And the statement is that those elements will not contribute to the cohomology. This has a name. So we call that, so this is C of C minus subcomplex of the of that subcomplex generated so it's X alpha A or alpha positive root. So this is like element in the image of En and I N. Okay, so alpha Z. This complex is structured. So corollary is that it's concentrated in cohomological degrees. So why that? So, I mean, yet again, our problem with using the argument about the associated graded comes from the fact that those elements can have infinite, like can be unbounded. We said that the span of those elements will be contractible. We're left with bounded elements. And then we can use a spectral sequence argument to show, to say that the cohomology is again in degree 0.
So this theorem is an isomorphism of vertex algebras.
Which isomorphism?
The proposition that the semi-infinite cohomology is functions on the Slotoway slice.
Yes.
Is it also of Poisson vertex algebra? Is there a Poisson
yes.
vertex algebra structure?
Oh yeah, yeah. I mean,
semi-infinite.
I guess I should have mentioned that. Yes, like associated graded is isomorphic to that as a Poisson vertex algebra.
Okay.
So,
and how do you get the Poisson structure on the semi-infinite cohomology?
So,
without knowing this isomorphism.
I mean, the point is that our differential is compatible with vertex algebra structure. Poisson vertex algebra structure is just a vertex algebra structure. If it's compatible with that, this has a Poisson vertex algebra structure.
Great, thank you.
Okay, so in the 2 minutes left, I could say something about the W-algebra. Here's the statement. How do we get all of going back to the finite, how we can deduce the finite case from all of that? So here I am. Algebra. Affine W-algebra is just a finite algebra to change. And kind of proof, how do we see that? So I guess U algebra is compatible with tensor product. Already know that U of the enveloping algebra of G and U of the fermionic various algebra is default algebra, I guess. So the like the U algebra, so U algebra applied to the semi-infinite complex, or let's write it in the terms of the resolution, algebra applied to that is exactly the classical BRST complex. That's it. So,
Thank you.
I mean, just what happened to this J mu here? Yeah, with this proposition, so there was some action about jets of projection from G star to N star.
yeah, I mean, the standard was just that you can look at this complex and you can say take the first and third component.
Yes.
They just compute causal resolution of a specific subvariety. And we're saying this subvariety is defined by a regular sequence. This is identical to the finite case. You just take jets of the finite case. In the finite case, you only have cohomological degree 0. And we're saying here too. That's all. You can write down the equations defining the like the inverse image of mu, and it's going to be same equations for the finite case, and then a bunch of equations of like t to the n times the generator equals 0. So yeah.
Let's thank our speaker again. Thank you very much.